Hello and welcome to the third video of this exploding wire series where we're going to begin to model the phenomenon of the exploding wire by using some simple classical relationships. Let's begin by modeling this system as an RLC circuit as was discussed in the previous video. And the most common way to activate this electrical circuit after the capacitor has been charged is by the means of a spark gap, which is basically a device that looks like a capacitor, and you trigger it using a high voltage, and basically you fire a spark onto one of the terminals, and this begins the ionization of the air inside of the spark gap, or whichever gas you have inside of the spark gap, and then this triggers a large avalanche effect, and then you have a large spark going through these main conductors. So the spark gap is a very fast switch, and it has its own advantages in relation to mechanical switches. And we are going to consider that the time of triggering of the spark gap is in the order of 200 to 300 nanoseconds. This is what the data sheet of the manufacturer tells us. And we are basically releasing the capacitor from its initial condition, which is the capacitor being charged. So the resistance of the circuit is comprised of many components. We would like it to be only the resistance of the wire itself, but in fact, we have all of the other components here have their own resistance, and this is called the ESR, which stands by equivalent series resistance. And the inductor and the capacitor will have their own ESRs, and we hope that they are small in relation to the resistor, and indeed they are in the order of less than 10% of the value of the resistor itself. And we also have a little bit of radiation resistance, because this system will act as if it was an antenna, and it will radiate some electromagnetic waves during the pulse that explodes the wire, and this extracts energy from the system, and you can model that by a resistor. But this resistor is very small, so we might as well disconsider this and consider the radiation resistance close to zero. So you got to remember that everything is, to some extent, some RLC circuit. So the capacitor contains some ESR, as we talked before, but it also contains some internal inductor. And this is actually you can buy fast capacitors, and fast capacitors will have very small inductances, and that's the reason why you gotta, when you're doing the selection of your system, you gotta select a capacitor that has a low inductance, so your system will be fast enough. So we model this RLC circuit with the classical second-order differential equation that I'm showing here, and there are various different versions of this second-order differential equation. Here I'm showing the version that is based on the charge on the capacitor Q, and remember that the derivative of the charge in relation to time is the current in the circuit. And of course, we are here assuming that the current is constant throughout all of the circuit. So we are assuming that this current I is actually the same value everywhere, which is not exactly true, but you know, there is some phase difference. But for the frequencies that we're talking about here, the phase difference is going to be in the order of less than a degree. So this is a pretty good approximation in this sense. The feature that the exploding wire has in relation to the other RLC circuits is that R is a component that is changing as the wire changes. And by this, I mean that the R is increasing as the wire undergoes the process of heating. So while it melts, evaporates, and becomes plasma, there is some variation in the wire. So the resistance basically increases as it heats up. But when the plasma ignites, then you have a sudden decrease in resistance, and these will affect very much the behavior of this RLC circuit. And how does it do that? So the frequency response is not that trivial. The natural frequency of the system that is very easily calculable by this relationship here is not going to be the only frequency that is going to be shown in the system, because the natural frequency is basically dominated by this term here, which is the second order term. But on the other hand, we have this first order term, which is the damping term. And as R increases, this R over L term increases and it becomes dominant. So if R increases fast enough, then and we would like it to increase fast enough because it's exploding, right? So we would like R to increase fast enough, so R will dominate and will comprise of a very large chunk of the frequency domain transient response of this system. So the questions that arise here are basically how can we predict the behavior of some given system, right? And what is in the end the bottleneck of this explosion? Is it the electrical event? Is it the thermal event? Or is it the expansion of the vapor? So we don't have much control for these two events because they are mechanical events. So the only things that we can do here is changing the wire dimensions and changing the wire material. But we have a lot of control on the electrical current rise by the means of tweaking the variables L, C, and the voltage across the capacitor. So the question is, how will it make a difference? Will the system produce a stronger shock, whether it is faster electrically? And if so, which knobs can we tweak? So can we tweak C, V, L, and whatever can we tweak here? So this is the question that I'm asking here, and this is the design question that must be answered by some sort of prediction algorithm. So this researcher Tucker developed in 1975 with some strong simplifying assumptions a way to derive the resistivity of the wire, which is required to derive the resistance of the wire, right? So the resistivity of the wire changes as the wire changes, and he wanted to predict the resistivity based on his experimental data. So he came up with this concept of action, and action is represented by this letter G, and the resistivity is supposed to be a function of this action. So he defined, through his own calculations, action as being the integral of the current squared dt, which is proportional to the specific energy that has already run through the wire. And this is divided by the area of the wire. And you can see here that the area is actually outside of the integral, which means that the area is considered here to be constant, which is completely untrue, right? Because as the wire is expanding and undergoing melting and afterwards vaporization and plasma expansion, we know that the area, the cross-sectional area of the wire is gonna increase. It's bound to increase. And here he is considering that the area is constant, which also means that he is basically linking these variables, and although the area is increasing, the overall effect is that it's inside this resistivity. So let's take out the area out of the integral and consider it is constant and equal to the initial area in the beginning of the explosion. So what are these simplifying assumptions? So he considers that the specific heat is constant. And we know that this is not, this is completely far from the truth, right? And he also considers that the resistivity is a linear function of temperature, which is completely untrue too. So, you know, these simplifying assumptions are very constraining, and they simplify the problem perhaps too much, but as a first glance on what is going to happen, they actually predict the experimental data pretty well. So that's the reason why I'm showing them over here. So the model, according to the author, is valid until the current density J is less than 0.1 teraamp per square meter. So we have to bear in mind that this is a very small current density in by nowadays terms of exploding wires. So this is how this resistivity versus the specific action curve looks like. This is extracted from his own article. And you can see here it increases until the point where so here we can say that the wire is solid, and then it melts and becomes liquid, and then it begins vaporizing. So this is the vapor phase, and then the plasma ignites, and then the resistivity keeps on falling all the way. So in order to actually make a small piece of software that would predict what would happen with the wire, I looked up. There is an article from this author here that he basically he performed his own comparisons with his own experiment against the predictions from Tucker's data. And he gave in his article all of the values that we need in order to perform our own predictions. So this is the prediction lines that he came up with in his simulation based on Tucker's data. And I wrote a small specific MATLAB code to predict this, to perform the same predictions. And these are the curves that I obtained with my MATLAB code. And you can see that they pretty much match very closely the curves from Mao. So this was a way of me sort of calibrating my own MATLAB program so I could perform my own predictions. So we gotta bear in mind that Mao's exploding wire was the current density was in the order of 0.3 teraamps per square meter, whereas in the experiment that Jack built, the current density is in the order of 1 teraamps per square meter, which is one order of magnitude larger than Tucker's data. So we don't know how much we can actually apply Tucker's data to our experiment. But reading the article from Mao, we can he discusses that the predictions are not exactly entirely matched by the experiment, but you can see here in this graph the comparison. So in the right we have the experimental data, whereas in the left we have the predicted data, and you can see that although the shapes of the curves are pretty much closely matched, the numbers, the values of the numbers are not exactly the same. So for example, the current here, it tops at roughly 10 kiloamps, whereas in the simulation it goes all the way to 12, so this is a 20% difference. Whereas in the voltage here tops at less than 100 kilovolts, whereas in the simulation it goes all the way to twice as much, 180 kilovolts. And of course, Mao in his article, he mentions that this is actually a problem on his measurement system that is too slow to capture such peaks. So if his system is low, this is exactly the expected behavior. The peak would go down and would widen in comparison to the actual data. So it might be possible that the simulation is actually correct in this sense. But on the other hand, we don't have the transfer function of this outdoors measuring device, so we're not actually sure, right? We can't assess whether how much of this is actually true. So why am I criticizing this method so much? It looks like it predicts the experimental data so well, right? It actually doesn't indicate when the process is over, and this is really a very strong restriction on this method. So here is the curve from Tucker again. This is my version of the curve that I came up from his experimental data, and you can see here that this point is just when the experiment from Tucker's data happens to be over. And actually there is some extrapolation. The experimental data ends up roughly here. So we don't know if our experiment is going to be over here or is it going to go all the way through here, and we don't have any sense of time dependent effects. So we don't know whether if we made our experiment faster, if this peak would be different, if it would move in the action axis. We don't know because this is just a snapshot of Tucker's experiment. And they barely answer the question of how strong is the shock. And I'm putting these barely answer the question because if you run the experiment for long enough, the energy transfer is bound to be 100% of the capacitor's energy, because there is no other sink of energy in this system, right? Because this is just an RLC circuit. So if we don't know when R vanishes, which is exactly when the wire explodes, right? So we don't know when R vanishes, and because we don't have a definite end in time here, and therefore we can't predict when the experiment is over, so we can keep on going and dumping energy on this R, and therefore we don't know how much is going to be the efficiency of the energy transfer. And this is a very strong impairment on Tucker's method. Okay, so I'm going to show you here a little bit of this MATLAB code so you can see and how I'm going to play with it. So this is exactly the data from Mao's experiment. We have the inductance, capacitance. I placed a little bit of equivalent series resistance because we have these components as we discussed before. And here are the geometry parameters of the wire. And I'm not gonna bother you with this bullshit, but basically it uses the ODE45 solver from MATLAB to solve the differential equation that I showed you in the slides, and then it plots out all of the parameters through time. So let's give it a shot. It's exactly the same parameters as Mao's experiment, and you can see here the curves that it outputs. And let me show you here. It actually shows you what is the efficiency of this experiment, and you can see here that this value is actually very unrealistic given mouse data and also given many other experimental data. So 71% is actually kind of impossible for this, I guess. I'm actually giving a guess here. We are used to orders of magnitude in the order of like 30 to 20% or even less. And this is actually, the efficiency here is only 0.71, because even though I wanted the simulation time to be 10 microseconds, we run out of data, so the simulator clipped at 3.2, roughly 3.2 microseconds. So you can see here that the action G, this red dotted line here is when we run out of data, and it shows us that we actually run out of data. And this green line here is where the peak on the action curve happens, and it coincides with the peaks that you see on the other plots. So if we had more data, I assure you that we would hit the 100% efficiency. Of course, not 100%, because since there is some value to the ESR, we can see here that some very small, tiny little amount of energy is actually being dissipated in this ESR. So you can see the red curve, the dotted curve here that you barely can see is the energy that has been dumped into the ESR, and you can see here that it is in the order of 6 joules compared to the wire 280 joules. So it's negligible. I would say it's negligible. And but I want to play with the parameters here. So now we can see that first efficiency is in the 70% range, and we have this current going. This current going to roughly 12 kiloamps, and the event lasts 3.2 microseconds before we run out of data. So what happens if we multiply the capacitance by 4 and divide the voltage by 2? So this keeps the energy the same, right? Because energy is half CV squared, but it makes the system 4 times lower, right? So let's run the simulation again, and let's see what happens. So now the curves look much different. We didn't run out of data. You can see here that we actually run the simulation all the way to the 10 microseconds, and we still have a little bit of data here. And the peak current now it's much smaller, is in the order of like 9.5 kiloamps, and we have a lot of the event is happening in this plasma phase. But this is a very long time for a plasma phase. So we have like between 4 and 10 microseconds. So by this time, the plasma has already expanded a long time ago, and this curve doesn't look in this shape anymore. So I'm opening your eyes to these features of the experiment that Tucker's data cannot describe. So let's go to the other side, and so let's come back to the initial condition of 2 microfarad and 20 kilovolts. So let's now divide the capacitance by 4, which means that the capacitance now becomes 500 nanofarads, and multiply the voltage by 2, which means we kept the energy the same, and now we have a 4 times faster system. So let's see what happens. Now, of course, we run out of data sooner. We consume all of Tucker's data, but we still don't have much sense on what is happening here. Of course, the peak current increases slightly a bit, but we don't have much sense on whether this is beneficial for the experiment or not. So we don't know if this is going to produce a stronger explosion or not, because the efficiency, if you see here, the efficiency is, it's in the order, in the same order of magnitude. We didn't actually have an increase in efficiency, so that's the reason why I don't actually trust this kind of simulation to predict how effective is going to be the exploding wire. But we have the sense that if we make the system faster, it is bound to produce a stronger explosion, because we will not allow the system to expand before we dump as much energy. But we'll not be able to optimize this in the sense of like what is the best. So one thing that I would do if I were designing the system is to reduce the inductance the maximum that I can. And you can see here that the inductance is an independent parameter, so we can actually reduce it as much as we want. So for example, if we bought a capacitor that is low inductance, and we can buy low inductance capacitors which inductance is as low as 10 nanohenries, and capacitances as low as 100 nanofarad. And of course, in order to keep the energy the same, we have to increase the voltage. So let's just do a simple calculation here. We have 400 joules, which multiplied by 2 and divided by the capacitance of 100 nanofarad, and then we take the square root, we get the voltage of 90 kilovolts roughly. And then we run the experiment again. So let's assume that we connected the capacitor directly to the wire, and of course it's not very realistic. We have some inductance, so this inductance is very unrealistic. It's on the low side. But let's take a look at what happens with the experiment. So the first weird thing is the efficiency is kept the same, which is ridiculous. And you can see that the curve for the resistance, all of the curves get skewed up. The current rises, rockets out to 120 kiloamps, which is probably true. And you see here that the we run out of action data before 0.225 microseconds. So this is a 10 times faster experiment, and of course we expect the experiment to provide a much stronger explosion. But how much stronger? Where is the limit? Where does it asymptote and we can't produce any more any stronger explosion? We don't know. So this is the limitations of this model, and I would like and I think now you can see the limitations too. So I'm going to leave you with the references that I have here. And, well, thank you very much for watching, and I'll see you next time. Bye-bye.